All right, I guess we're about ready. Go ahead and chat me your first and last name in the chat box, please. So we'll have it for roll. If you haven't already, it looks like only two of you already have. It's about time to get started. I'd advised you I was going to try to make some videos on chapter 25, and I'm still planning on doing that. Not necessarily chapter 25, but I'm going to continue working straight from the examples that I can fit in into chapter 25, and then maybe I have to make a few videos initially on chapter 26 or something like that, so we can get ahead a little bit. I really want to try to get you guys through chapter 31. Covering chapter 31 very, very lightly, but just at least exposing you to it. So that's what I'm really trying to uh, get. I won't be horribly upset if I only get to 30, but even 30 is kind of not the best thing for me to do. So I'm going to do my best and try to do it in such a way that it's fair and not painful for you guys. But let's go ahead and get started by me sharing my screen. I'll ask again, does anybody have any questions before we get started? Don't forget, you will have a face-to-face test that you guys will have to do next week. I will have it posted probably Monday, but at the most it'd be Monday night. And then there will be an online test posted as well, and you could do the face-to-face test before Thanksgiving if you wanted, but you could also do both the face-to-face or the online after Thanksgiving, because I'm going to give y'all till Tuesday night at 11:59 to get those done. So if you find that I've set it up wrong or something like that, make sure you send me a text. That's the kind of goofy thing that I do quite a lot. So hopefully I won't, but I'm okay with you guys texting me to let me know I screwed up. I don't want to get offended by that. I just take it as you guys helping me. So it looks like no one has any questions, so I'll go ahead and share my iPad screen. And as I advised you guys, we are in chapter 25, and specifically, we've already done examples 25:1 through 25:9. That means the example we're getting ready to work now is an estimate example, 25:10, that's from your book. So the ideal scenario here, since I didn't have time to write the actual questions a priori, is really to look at your book in real time if you can and just read the actual question. I'm not allowed to post it like in my video because that would be a copyright issue, but I can certainly sort of discuss the solutions. I think it's okay to read it, and mainly I think it's okay to read it because they're not going to listen to words to find out whether I'm violating it. They're more worried about me showing stuff. So, anyways, it says lightning is a spectacular example of electric current and natural phenomenon. There's much variability to lightning bolts, but the typical event might transfer 10 to the ninth joules of energy. I'm going to write that down because that's a number that we're probably going to use. So I'm going to say delta E is equal to 10 to the ninth joules. That's what I'm writing down first. But a typical event might transfer 10 to the ninth joules of energy across a potential difference of perhaps 5 times 10 to the 7 volts. So I'm going to say delta V. Delta V is equal to 5 times 10 to the 7th volts, which you know is on the order of 50 million volts during a time interval of about zero point 0.2 seconds. So I'll say delta T is equal to 0.2 seconds. Looks like they're doing 1 and 2 sig figs, pretty much 1 sig fig everything. Use this information to estimate A, the total amount of charge transferred between cloud and ground, and B, the current in the lightning bolt, and C, the average power delivered. So for part A, and this is example 25-10. Sorry for putting that down there. In part A, they want to know how much charge is delivered. So delta Q is what they're looking for. In part B, they're looking for the current. So I is equal to question mark. And in part C, they're looking for the power. So we'll begin as follows. So one equation that you might not recall is U is equal to Q delta V. So that's a relationship between energy, charge, and voltage, which happens to be very relevant here because we're talking about a certain amount of energy and we're asked about a certain amount of charge and we're given a certain amount of voltage. So that's one thing we could use. I can also say that Q is really delta Q for this problem, so that kind of helps us a little bit. I can also say that I, the current, is delta Q over delta T, and I also say power is equal to energy divided by time. So those are some of the things we're going to use. Like I said, we're supposed to find out specifically the total amount of charge transferred between the cloud and ground. Since we found that the energy was 10 to the ninth, we're going to use U equals Q delta V. And we're going to say 10, whoa, evidently I'm going to say 19. I'm going to say 10 to the ninth joules is equal to Q times the voltage difference, which will be 5 times 10 to the seventh volts, like that. So we can get Q, which is delta Q, which is equal to 10 to the ninth joules divided by 5 times 10 to the seventh volts. Remember, a joule or a volt is a joule per coulomb. So when we actually divide this, we will actually get coulombs out as we hopefully expected. So that's 1 e to the ninth. Notice that's how I put in 10 to the ninth. It's very easy to make a careless mistake on that one. I just call it 1 e to the ninth. Uh, if you do 10 e to the 9, that'll actually make 10 to the 10th, so that's a problem. So anyways, 1 times 10 to the ninth divided by 5 times 10 to the 7th, that's going to give us on the order of 20. Actually, it'll give us exactly 20. And we're going to say that's 20 coulombs. So a typical lightning strike is not unreasonably thought to deliver on the order of a few dozen to maybe about 100 coulombs of charge. So that's not quite as much as you thought, but again, that's more reminiscent of the fact that a coulomb is a really big amount of charge. Let's look at part B now. So for part B, we're supposed to find out what I is, and as I advised, I is delta Q over delta T. We did say that it would take about 0.2 seconds, and we just discovered that it delivers about 20 coulombs of charge. So I'll write 20 coulombs, and I'll divide that by 0.2 seconds, which remember is the same thing as 2 over 10. So that's going to make basically 200 over 2 coulombs per second because again, like I said, 0.2 is 2 over 100. So I'd basically multiply by 100 over 2. That gave me, whoa, that gave me 2000 over 2. Sorry about that. Yeah, that gave me 2000 over 2. Actually, that's over 10. No wonder. Sorry about that. My arithmetic skills are sometimes really awesome, but other times they really are showing that I'm kind of a moron. So anyways, that turns out to be 200 coulombs divided by 2 seconds. And of course, that is 100 coulombs per second, which equals 100 amps is equal to I. So that's our answer. So not only is it not uncommon for a bolt of lightning to carry on the order of a couple dozen to 100 coulombs, but it's also reasonable for it to carry about 100 amps. And obviously that's enough to hurt somebody. Yeah. Now, here goes part C. In part C, they just basically want to know the power, which is how much energy delivered per unit time. So what I can do is I can just say power is delta E over delta T, which I'm going to say that's 10 to the ninth joules over 0.2 seconds, which obviously is, let me show what I did a second ago. This is 10 to the ninth joules on top. What I'm going to write down here, I kept saying 2 over 100. I don't know why I was saying that, but it's 2 over 10 because it's in the first decimal place. So this actually becomes 10 to the ninth joules times 10, obviously to the 1, divided by 2. And this top is joules, excuse me, like that. So we're actually getting joules per second, which is watts. And obviously, what we're going to get is 10 to the 10th times 0.5. So 0.5 times 10 to the 10th joules per second, which is watts. So we can actually multiply this by 10 if we divide this by 10. And in so doing, we will basically get 5 times 10 to the ninth 5 times 10 to the ninth watts, and that's the power delivered by this lightning bolt. Anybody have any questions on that one? Okay, so that's just a rough estimate. We've got a pretty good look at that now. This would be called 5 gigawatts or 5 gigawatts. I call it giga, but you all know that watched Back to the Future, they called it giga instead of giga. So I'm okay with you calling it that. Anything I can get my students to do to make them say something about physics, I'm okay with it. So even if it's mispronouncing something, which again, I don't really know if that's mispronouncing, so I don't want to get too high on my horse here. So in section 25.6, they talk about things like, for instance, fuses, circuit breakers, GFCIs, which means ground fault circuit interrupt. All of these are really good devices, and they're surprisingly, in some cases, very mechanical, in other places, very automated. But I'll just tell you that basically, if you wanted to make a fuse or make fuses for a living, what you could do is you could basically look for the cheapest metals that can conduct electricity, okay? And then maybe you invest in some machining equipment to cut it down to whatever sizes you wanted, or maybe you invest in a 3D printer for metals that can print the cheapest metal you can find that conducts electricity well and doesn't corrode too horribly. But then you would basically see how much current you can put through it for a given length and width and thickness. And when you do that, you can slowly work it up and find out exactly how much current it takes a given measurement of this new metal that you have to actually melt all the way through. Now, if you can find a way to design that piece of metal wide enough or thick enough, or both wide enough and thick enough to handle right at 20 amps, then you could make a 20 amp fuse. Obviously, that'd take a lot of trial and error, or it could take, you could work out the math and sort of figure it out yourself what's going to be there. But the main thing is you would have a way of doing it. And then all you know is that for a given setting, like a fuse for 30 amps, that would be a piece of metal that allows 30 amps, but right around 30 amps is going to melt completely through and open the circuit. So that's the way a way a fuse can be worked. Obviously, you have to complete the circuit by letting the current go through the actual ribbon of metal that's in the fuse. But you could also do it with, for instance, a circuit breaker, which you can see in your book. They use a diagram where they're using a bimetallic strip that the current actually goes through. So the bimetallic strip goes through this, or excuse me, the current goes through this bimetallic strip that's vertical. But as the temperature of a bimetallic strip changes, one side will, or both sides actually get longer if it's getting hotter, but one side will get longer quicker than the other, and it'll cause it to bend like that. Well, if you work with that enough and work out the details of what actually happens at, 15 amps or 20 amps or 25 amps or 30 amps or 40 amps, whatever settings you would want your circuit breaker to be, you can trial and error figure that out to where eventually whatever the setting is for the particular circuit breaker that you want, let it be 40 amps, for instance, you can fix it so that exactly at 40 amps, the bend is just perfect where it can fall into a little dent in some metal. That dent in the metal will allow the metal, which is pushed down by a spring, to push down like that, and then that disconnects the circuit. That's literally what happens with this particular type of circuit breaker. So that's another way of doing it, brilliantly mechanical. There's other ways as well. There's ways you can actually make sure the current just automatically connects to ground once it gets too high. That can be something that can be a lot quicker than a mechanical device, so that helps a lot as well. But anyways, that's what they're talking about regarding power in households. And they start off with an example 2511 that I think is really good. So we're going to do that one now. Example 2511. And this is what I tell my students is probably, or at least the first part of this problem, is probably the single most important thing I can teach you for a physics class for your everyday life. Okay, so in our physics class, a lot of times we have a lot of stuff that's very interesting, very helpful, very important, all this stuff, especially to careers in engineering and medicine and chemistry and science and stuff like that. But in this case, we actually have something that's really, really quite fruitful for people that just are going to own a house. The main thing being, for instance, you're going to have extension cords, you're going to have tools, you're going to have things that run on extension cords, even, things like as simple as a stereo. So if you have extension cords, you need to be able to know, hey, if someone tells me the power a certain device has, let's say a hair dryer or a space heater or a stereo or something like that, if they tell you the power, you should be able to figure out exactly how much current is needed to run that device. And then you should be able to just go and find a appropriately sized extension cord so that it can handle that much current. And you should always allow a little safety factor. So for instance, if your calculation shows that you need 15 amps, then probably be better to look for something that holds at least 18 amps, if not 20 or something like that. So in this question, what they're giving us is four particular items. And what they're telling us is that there's a light bulb, and the light bulb uses 100 watts of power. So that's 100 watts. I'm going to treat all these as like they're significant digits up to the decimal place. So this one would have 3 sig figs. Then there's an electric heater, and in that case, there it goes again. In that case, the electric heater, which I'll say EH, actually has a power output of 1800 watts. And then there's the power of an amplifier, which I'll call P sub A. Now that one's pretty minor. That's only 175 watt. And then finally there's a hair dryer, and this is very reasonable, by the way. So the power of the hair dryer, I'm going to call PhD. Uh, that's actually 1500 watts. Okay. And what they're asking you in this is imagine all of these items are plugged in to the same leg of a circuit. So, for instance, when your electrician comes out to build your house or your apartment that you happen to be living in, they will basically divvy out the control panel or the circuit panel that might be in a bedroom, hopefully not, but more like in a garage or something like that. You usually don't put it at least in a kid's bedroom. But if they did lay it out properly, then they'll have a certain number of circuits that'll be balanced in such a way that you're not overpowering one side of the breaker versus or one side of the panel versus the other. But what you got to do is you got to decide, okay, what light receptacles are on what circuit. And then you got to sort of keep those all together because there's a very distinct law in the code about how much current your light receptacles should get. And then there's also limits to how much current you can send on one particular leg of a circuit. So basically, each quote unquote leg of the circuit panel is controlled by one fuse or one circuit breaker. Okay. So what we're imagining here is all of these items, the light bulb, the electric heater, the amplifier, and the hair dryer are all plugged into light receptacles on the same leg. And what we're trying to figure out is what is the total current drawn, and if that's the case, what kind of fuse would we need? So what they're asking here is they say, will a fuse blow? Determine the total current drawn by all the devices in the circuit in figure 2520. Okay, so let's start this by solution. So here's what I'm going to use. We know that power is what's been given here, and there's a bunch of versions of power. The most common one that's used is P equals IV, but I want to remind you that it's also I squared R, and it's also V squared over R that counts as power. I'm going to use P equals IV because I'm basically knowing that the voltage of a house we generally call 120, 125. But to err on the side of safety, I'm going to assume the house voltage will be a root mean square value of 120. So I'm also going to say V house, uh, which I'll just call V sub H, is equal to 120 volts. And I'll call this RMS because it really is the root mean square value of the voltage. Okay. So what we know is that when you wire a receptacle, you can look at a receptacle, for instance, and you'll see that it has one long side and then one short side and then the little mouth like that. Again, I don't remember, but I check it every time I go to install a light receptacle, for instance. It says right on the back, you know, white goes to this, black goes to that, bear goes to this, or green goes to this sort of thing. But the main thing you need to know from that is when you look at a light receptacle, I'm not going to take the time to draw the slits on everything, but when you look at it, you'll see it's basically a little box like this, and you basically have some very specific screws on this side. Like one side's brass and the other side's silver looking. So I'm just trying to show you that there's something different on the two sides. Now there's also usually a screw somewhere over here or something like that, and that one's actually for ground. So I'm going to do a double color thing so you know it's not supposed to be a red or a blue. It's sort of a mixture of the two. So if you have two of these, then the next box, of course, is going to look the same. And again, you're going to get the same little screws on the left and the same little blue screws on the right. And what those screws mean, by the way, is they mean that basically the slots on the right hand side go to the blue screws and the big slot on the left hand side go to the red screws. So when you go to connect a part of a leg of a circuit, as we talked about earlier, what's done is you take a wire, I'm going to use black here, and you connect from the power supply to one side. Again, I'm saying black, but I'm not necessarily saying that's the color of the wire. I just happen to use that color for the wire. And then the other wire, which will be a distinctly different color, I'm going to say, let's see what color. I'll use nah, green's kind of dangerous. I will use a crappy brown color. So another wire from the power source comes here, and then basically the bare wire or sometimes the green wire comes to uh, that little screw on the top, and that little screw on the top basically corresponds to the little mouths on the light receptacles. That's why I'm drawing it green like that. Okay. So that's actually your ground. And if you followed that wire all the way back, you'd find that eventually all the little green or bare wires in your house all come back to one aluminum bar in the back of your circuit panel. And then that aluminum bar has a wire that runs from it and goes through the wall of your house and then goes somewhere along the wall of your house to some spot. And then it goes straight down to the ground. On there, you'll find a clamp that's clamped on about a 3/4 inch thick copper rod. And that copper rod, I know, is at least 6 foot, but I think code requires them to be 8 feet. And it's been driven into the ground 8 feet deep, and that's the ground. So literally, ground is literally connecting to the ground. All right. Now, what you do is these both come from the power. So these are coming from the power company. Say, I'll do this to indicate that. Said from power company. So all of these, and I drew a current on there, or I drew arrows on there just to show which way they're going. I'm not just necessarily saying that current's going through there. In fact, current would very possibly go a different way on that green one. But the main thing is I wanted you to see that this is from the power company. Specifically, it's actually coming from the circuit panel, and the circuit panel is being fed from the power company, but that's okay. Now, the next wire is another black one, and you have to connect this light receptacle to any other light receptacle. So you'll take the black wire and connect it to this red terminal, and you'll take the putrid baby crap green, orangish wire and connect it to the blue one over here. And then you'll take the actual green wire, and that's going to run to the same thing as well. And if you have more receptacles, then you're on this leg, which you certainly do, you're going to run it to another red screw, and you're going to run the baby crap yellow to another blue screw. So you can just imagine a blue screw being here, and you can imagine a red screw being here, and there's another receptacle coming, obviously. So that's the way the circuits are worked out. And like I said, you can see that this is clearly a parallel circuit. So you can look at it as if there is we use this instead of the normal battery symbol when you're using AC because it looks like a little sine wave. But what you want to think about is this wire comes out this way, and then this resistor is one light receptacle, and this resistor is another, and this resistor is another, and this resistor is another, like that. So that's pretty much what this, at least this part of the circuit looks like. It'll have four receptacles that are each in parallel, so that what you see is each of those things get a certain amount of current, and if you add those four currents together, that'll be the total current coming through, of course, the circuit breaker. I didn't draw the circuit breaker on here, but I can put it right here and just say this is a circuit breaker. Could also be a fuse, of course. But the main thing is it is protecting your house from burning down because the wires and everything are put in the walls according to code of a very specific size. Those sizes dictate a very specific amount of current goes out, and then code requires you to have a circuit breaker or a fuse that matches that setting. So if you didn't do it properly, there's some chance that you'll send more current through a wire than it's supposed to take. That would cause the wire to possibly melt through, burn the housing and the housing of the wire, and then of course possibly set the house on fire because it would be running right next to insulation, which they do a lot to try to make flame retardant, but still it's dry, it's paper, the nearby wood, dust, all the stuff in there, all that could ignite. So that's where we're going with that. So now what I'm going to do is I'm going to take and use each of these powers to calculate exactly how much current each of them are using. And with that, you can see the calculation that I said was so important. So I'm going to say I for the light bulb is going to be the power divided by the voltage. And of course, the power for the light bulb is 100 watts. And the voltage, of course, is 120. Again, this is root mean square voltage. So when I divide 100 by 120, I get 0.833, if I remember correctly. Yes, I get 0.8333 amps. Okay, remember I'm assuming that all the digits that they gave us before the decimal are significant. So that's one current. We also have a current from the electric space heater. And of course, that one is also P over V, but this one has a P that's equal to 1800 watts. And then you divide that by 120 volts. I think this one's 15. Let's see, 1800 divided by 120. Yes, that's 15.00 amps. Obviously, three sig figs there. Now I have the current I for the amplifier, which is again power divided by voltage. In this case, the power was just a measly 175 watts, but the voltage was still 120. So 175 divided by 120 gives me 1.45 and then it continues 833 like that. Now, technically, we only have 3 sig figs, so I'm going to call that 1.46, but I will carry 1.4583. Finally, we have the last current, which is the current through the hair dryer, and that one's 1500 watts, again divided by 120. So 1500 divided by 120 gives me 12.5 amps. So that's the amps in total. So I'll say I total, which is what the circuit breaker is defined in terms of, is going to be 0.8333 plus 15.00. Notice I'm leaving the units off. They're all the same, so it's not too much of a problem. 1.4583, and then 12.50. And all of this is going to give me 2.5 plus 4, 1.4583 plus 15 plus 0.8333, like that. Now, what I see is all of this should be rounded to no more than evidently 1 decimal place is all the sig figs we have. So this becomes 29.792. That's 2 extra sig figs. That's the amps. So I total is equal to 29.792 amps, which obviously we would call 29.8, and that's fine. That's the answer. So in this case, as a bare minimum, you'd hope that the breaker was 30 amps. But if it wasn't, it would certainly break if it was lower than that. I say break, it's just going to flip. Sometimes they do get damaged, by the way, but generally speaking, they should last a long time without damage. But it is possible literally for them to break. And when they flip, that's normally when it happens, is when something, is going wrong or whatever. So just like your book, you got 29.8. It said the heater draws as much current uh, as 18 100-watt light bulbs. For safety, the heater should probably be put on a circuit by itself, and that's a good estimate. That's one thing I like about Gene Coley's book. He gives us some good practical advice, tells you how to connect jumper cables and cool stuff like that. So, anybody have any questions on that problem or how we set that up to show you that the currents or that the breakers and everything, how the breakers protect the wires and then the receptacles are put in parallel? Okay. So I'll do another example. This is a short one, example 2512. This is a conceptual example. And in this one, it says a dangerous extension cord. Your 1800-watt portable electric heater is too far from your desk to warm your feet. Its cord is too short, so you plug it into an extension cord rated at 11 amps. Why is this dangerous? So, why is using an 11 amp extension cord to run a 1800-watt space heater dangerous? So we know P is equal to IV, and we know V is equal to VRMS, which is 120. Now, remember, I did tell you it's 120, roughly 125. In fact, if you put a multimeter on your light receptacle, you might read occasionally it gets up around 123 and stuff like that. But notice when we go to solve this for current, we get I is equal to P over V. So if you use the 123 or the 124 or 125, you would actually get a smaller current, and that would be the opposite of conservative. That would be a liberal estimation where you want a conservative estimate so that you are further likely to protect your home as opposed to further likely having a fire. So in this case, we're just going to take the 1800 watts. We already know what the number is. We just did it a second ago and we remembered it before. But the result is 15.0 amps, which is greater than 11 amps. So this is a fire hazard. I can tell you that honestly because I did the same thing. Specifically, I bought an extension cord and I knew exactly what size it was, but it turned out this particular case I had picked up one that evidently had been cross-shelved. Someone had taken it and stuck it in a slot with a bunch of other ones, but its amperage reading was too small for what I thought it was because on the rack it suggested it was up to 18 amps or no up to 22 amps I think is what it was, and it turned out that I was actually using a much lower rated cord and I was using it for a edger out in my front yard, and I felt something felt like a wasp or bee sting in my pinky, and I looked down and realized the wire, the extension cord, was actually so red hot that it already melted through the housing of the wire and was burning into my finger. So yeah, it does happen and it happens quick. So be careful with that. Anybody have any questions on this one? All right, we're gonna go ahead and line that off for now. What I wanted to tell you is that we do have alternating current, and I need to give you some of the details about that. And I'm not necessarily going to derive them or anything. In fact, there's not much to derive here. It's more or less just definitions. So what I'm going to tell you is that this is how AC works. Whoa, Nilly. I'm going to throw that away because that was my iPad trying to make my drawings prettier. So this is AC power in the US. Okay. And I was specifically saying because the US, because we do a different power grid than, for instance, Europe does. I think Canada and Mexico might be using similar things to us, or at least more similar than Great Britain does, but I'm not sure. I haven't plugged anything in over there, even though I have been to Mexico a couple times. But AC power in the US basically looks like this. We'll have a plot, if you will, of voltage on the vertical axis, and that, of course, would be measured in volts. And then that's going to be with time in like seconds on the horizontal axis. And what the voltage looks like is a perfect sine wave, and it really is pretty close to perfect. It just turns out to be really easy to make that. And in fact, all these peaks are all roughly the same height, and all these troughs are all roughly the same depth, and they're the same depth as the other ones are height. So this is on the order of negative 170, and this is on the order of positive 170, plus or minus a couple volts or whatever. So because of that, we also call this V0, by the way. That's what we use for our peak voltage is V0. Okay, so if you take that into consideration, then what we're saying here is that the voltage in AC will equal V0 times the sine of 2 pi F times T, which is also called V0 times sine of omega T, where omega is defined to be 2 pi times the frequency. But if you recall from last semester, frequency is 1 over the period as well. So you can also say this is 2 pi divided by the period. Now, in this case, the period would be roughly there. And if you're trying to look for a measure of what the voltage is, it turns out that an average would be bad. So if you want to calculate V average, what you might do is multiply by 1 over the period because you're actually going to introduce a period in it and you're going to integrate over time. So that's going to introduce a time variable to it, but you're going to integrate V0 sine omega t dt from t equals 0 to 1 period. That would be the way that you go about calculating the average voltage. Well, if you're looking at this, I suspect you probably can see that the average voltage will in fact be 0 volts, and you'd be exactly right. So that turns out not to be the best thing. A reason being is obviously it's just as much time in the positive as it is in the negative, and the positive part of the graph is the mirror image of the negative part of the graph. So clearly they're canceling each other out. So it's been determined that a better thing is to imagine squaring the voltage and then averaging that and then taking the square root of it so that you get back to the actual volts. So what we ultimately do is we say V RMS, and this is what it's defined to be. Again, you're doing 1 over the period. You're taking the integral from t equals 0 to 1 period, but now you're taking it of v0 squared sine squared omega t dt, and then when you're finished, notice the RMS means root, taking the square root, mean, taking the average, square. So you're taking the mean of the square and then taking the square root. So this is how you actually calculate it. And it turns out that when you do this integral, you get V0 over the square root of 2. So that's another important result. I'm going to box off this one. I'm also going to box off these important parameters. And I'm going to box this. Whoa, Nelly. I was going to box that off. I'm going to box off this formula just so you'll know really where it came from and that you can do it on your own. But the part that you need is the VRMS is equal to V0 over the square root of 2. Now, this also results in, for instance, the current I, which is actually equal to V0 over R, is actually equal to V over R. But we know what V is. V is V0. Of course, we're still going to divide it by R, but it's V0 times the sine of omega t. Again, the omega is 2 pi f. But now you can see that the I 0 is equal to V0 over R, and that I root mean square is equal to I0 over the square root of 2 because it's exactly the same type of function. So that's another formula we have. And remember another word for this V0 is peak voltage. And then there's another word that's often used, and they talk about peak to peak, and that literally means twice of 170, because basically it's 170 up and then another 170 down. So the total distance is 170 plus 170, which is about 340. So that's another terminology or another term that will be used. So we've got all that. Now you might wonder, what about power? Because we learned that power, of course, is equal to many things. We could say I times V is equal to I squared R. It's equal to V squared over R. But what would it be in terms of, for instance, AC power? Well, when you do that, you can say P equals, and your book chose to do I squared R for a good reason. I'm going to write that down, I squared R. Of course, we just figured out what I was, so we're going to write that as I0 squared sine squared omega t, like that. So that's the I squared, and then we're going to have an R in front of it as well. And if you look at that, you can realize that it's I squared I0 squared R times sine squared omega t. That's what the power is. That's not super helpful. But what we can do is we can see that the average power would equal 1/2 I 0 squared R like this, because basically now you can do the same integrals that I was showing you before, and we'll get a nice little formula like this, which tells us how we can go about getting a power in terms of I or V or R when I'm using the I0 as opposed to the root mean square. Notice the I0 would have been I0 over the square root of 2 and then times another I0 over the square root of 2. That's where the 1/2 came from. So it might make you sense that maybe we should be doing this in front in terms of root mean square, and you'd be exactly right. I will tell you that in general, the power or the average power on AC is equal to, I'll write out the different versions, but basically it's 1/2 I0 squared R. It's also 1/2 V0 squared over R. And you could, in principle, see that it'd be 1/2 I0 V0 if you wanted. And I was trying to look to see if your book even gave that one. I don't see it anywhere, but yeah, that definitely has to work. So we could also say it's equal to 1/2 I0 V0. So those are all valid power equations, and they kind of are crappy because now you got to think about a 1/2 and all that kind of stuff. But the good news is if you work all this in terms of RMS values, then you get a whole different set of values. You get P is equal to IRMS times VRMS. It's also equal to IRMS squared times R, and it's also equal to VRMS squared over R. So yes, guess what? Using the root mean square is a lifesaver. Anybody have any questions on that? All right, so we're going to look at another example now. Let's say example 2513 this time. Ow, hurts. Not getting much feedback. Do you guys have any questions? Am I just sort of blowing you away? I'm not wanting to do that. Hopefully this is just fairly straightforward material. It really should be. Okay, 2513 says this. Calculate the resistance and the peak current of a 1,875 watt hair dryer. So we're saying the power of a hair dryer is 1,875 watts. And what they want to know is they want to know R for the hair dryer. That's question mark. That's part A. They also want to know I0 for the hair dryer. So that's another part of A. And then in part B, they want to know what happens if you accidentally connect this to a 240 volt AC line in Great Britain. So B, what happens? And I don't know why I'm writing so small all of a sudden, but what happens if connected to a 240 volt line? So that's the question for part B. Obviously, we'll start off with writing out solution. And now in doing the solution, we need to be somewhat aware of what equations we might want to use. So for instance, they're asking for the resistance and the peak current. So my idea would be use the fact that the average power is equal to, let's say, I uh, root mean square times V root mean square. And that'll actually allow us to determine I root mean square, and then I root mean square is equal to I0 over the square root of 2 will allow us to figure out the peak current. So that's how we can get the peak current, and ultimately, once we have that, now we can also try to figure out the resistance. So we could have used another P formula in terms of the resistance if we wanted to. For instance, we could have used P bar is equal to V root mean squared over R, and that would work as well. That would get us R. So let's begin with part A. So with part A, I'm going to say P on average is supposed to be equal to IRMS times VRMS, and that's going to be obviously 1875 watts is equal to IRMS times 120 volts. So this gives us that IRMS is equal to, obviously it's going to be a little bigger than 15 because we know 1800 gave us 15, but in this case we're going to take 1875 and divide it by 120, and we'll get 15.625 amps. And of course, we really only have 3 sig figs at best to use there, so I want to underline the 2 and the 5. And that's not what we were asked for anyways. We were really asked for the I0. What we do know is IRMS is equal to I0 over the square root of 2. So from that, I can say 15.625 amps is equal to I0 over approximately 1.414, like that, because that's 4 sig figs. We're only using 3. That's enough. So this gives us that the peak current I0 is 15.625 times 1.414, which is, like I said, approximate square root of 2. So that gives me 22.094 amps is the peak current. So we've got that. Now we could just use basically the equivalent of Ohm's law, which says VRMS is equal to IRMS times R. Or, like I said, we could try to get the actual power version and use that again. Either of those would work. So let me show you just real quick. If we use actually, go back to purple. If we use the idea of Ohm's law, which is red, VRMS is equal to IRMS times R. I'm going to circle that again because I want you guys to remember that's one of the equations that you have at your disposal. But with this, I'm going to go ahead and say that the R could equal VRMS over IRMS. So we're going to take 120 volts and divide it by 15.625 amps. And when I do that, I get 120 divided by 15.625. That's 7.68 ohms. And we could put a 0 on the end of there and call that a non-significant digit. So that's actually one of our results. Since I wrote this one in blue instead of purple, I'm going to box it off in purple. So that's the other answer for part A. Anybody have any questions on that? Now, what's going to happen when we connect this thing to 240 volts instead of getting that special plug like we're supposed to get if we go traveling to Europe, for instance? Well, in this case, if VRMS is equal to 240, then what we're going to get is P, the power, is actually going to be IRMS times VRMS, and we know that VRMS is 240, but we also know that VRMS is equal to IRMS times R, and if we assume we have the same resistance, then we can actually use that last version to figure out what the actual IRMS will be. So I'm going to assume that that 7.68 stays the same. I suspect it would actually go up quite a bit because 240 volts is probably going to lead to twice as much current. Twice as much current is going to lead to a lot higher temperature of the actual tungsten or whatever they're using for the heat element. Therefore, that's going to make it so hot that the resistance will go up even higher. So it might be quite a bit higher, but we'll just do this as like a first order approximation. So what I'm going to say is 240 volts is equal to IRMS times 7.680 ohms. That means IRMS is equal to 240 divided by, that just happens to be the last answer I did. So this gives me 31.25 amps. That 5 is an extra sig fig. But notice that is well over, or that's right about twice as big as the current that we had in the previous case. So now I can calculate the power at 240. And in that case, it's going to be IRMS times VRMS, which equals 31.25 amps times 240 volts. So if I multiply 31.25 times 240, I get 7,500 watts. So that's how much power it's going to generate. It was supposed to generate 1,875 watts. Now it's getting essentially, this looks like it should be 4 times, roughly 4 times as big. So yeah, it's about 4 times as much wattage. That's going to obviously take a toll on the heating elements because they're probably carrying, like I said, twice as much current. Maybe they're not designed for that, and therefore they completely melt through and break if you're lucky. Or maybe worse than that, they actually do get that hot and there's no correction for it. So it just stays that hot and slowly melts through the housing that was never intended to be that hot. And then one day you have a little fire. So that's what happens. So yeah, it's not a good idea to randomly plug your electronics into receptacles in foreign lands. Anybody have any questions on that one?
No question, but just a house lesson I recently learned is that microwaves should be on their own. Um,
Oh, they're in circuit.
yeah, for that reason.
Yeah, they do have a lot of power, so they can take a lot of current. But I never knew that they were actually wired separately. I should have thought of that. But yeah, come to think of it, I've checked the power ratings on microwaves before, and that would definitely be consistent with that. I
Yeah,
think a typical one is 1,800 or 2,000 even.
yeah, we had a electrician come to our house and he was like, "Yeah, most people don't realize that, especially houses built in the 80s, but that should be on its own."
Yeah, the stove is another one, and the dryer is another one. You'll notice the dryer usually runs on 240 anyways. So, but yep, thanks for that, Carter. Appreciate it. Anybody else? All right, we're just about done. In fact, all I got left to show you is another example and another concept. I won't go through the derivation. The derivation is actually quite neat. I will solve the problem. That'll help you understand it. But basically, your book does a really good job at this. It introduces something we're going to be using later. It's called the current density. So there's a quantity that exists called the current density. It's normally treated as a vector quantity, and therefore I would say uh, J, at least in magnitude, is equal to the current divided by the area, the cross-sectional area of the wire, or as your book says, the I can be thought of as J times A. Right now, it's kind of hard to see the J as a vector quantity, but what we're going to do is we're going to introduce an equation that allows us to calculate the drift velocities of the charged particles. And when we do that, it's going to get a J in terms of a velocity, and then that's will be a nice time to relate it to a vector. I will also tell you that because of this I, the current, in the case where I had I is equal to J over A, that's sort of an average at best, but in reality, what you have is I is equal to the integral of J dot dA. So that looks a little bit like the left-hand side of Gauss's law because it is a dot product with a differential area element, just like Gauss's law. And that's how you calculate the actual current is you take J, which might be a function of time, it might be a function of X, it might be a function of theta, it might be a function of R, doesn't matter. You take that and then you integrate it over the whole cross-sectional area of the wire. So when I'm saying cross-sectional, I mean the current is running parallel to the wire. And if you imagine slicing that wire perpendicular to the current's direction, then you'll get a circular cross section. That is the cross sectional area, and therefore it's normally given by like pi r squared or pi d squared over 4. So along with that comes this other nice formula, which again we'll be using a little later. So we have that. What ultimately the results turn out to give us is really quite nice. You can look at the derivation, like I said, in section 25.8 of your book. So I'll say, so look that up. But ultimately, what the result is that we get a current which is delta Q over delta T from the derivation, and that turns out to be negative N E. E is the charge of the electron. N is the volume density of the free charges per unit volume. That's what that N is. And then this is times the area, cross-sectional area of the wire, times the drift velocity, like that. Now, that's not really the result we were looking for. We were more looking for the J, and of course, I is roughly equal to J times A. So we can just get rid of that A there, and we'll know what J is, and that's the equation. Even though I'm going to box this one off because you're allowed to use this as well, but that's the equation I'm really shooting for, is that the J vector is equal to negative N E times the drift velocity, like that, and now you see a vector quantity. Can anybody just think off the top of your head why the J equation has a negative in it? See if anybody's typing it in the chat. I see nothing. So remember conventional current versus actual current. Actual current is the direction that the electrons are going, which is opposite to the conventional current, which is where we're pretending positive charges are going around. So obviously the drift velocity is the direction that the electrons are going. And we want the current to go the other way, so we have to multiply the drift velocity times -1 to make sure it goes the opposite way. So that's what that is. Now, this equation looks really innocuous, but really the hard part is figuring out how to calculate that little n. So let me do an example for you real quick, and I've got two of them to do. So this is example 2514. Okay, and what we have here is a copper wire with a diameter equal to 3.2 millimeters, and it carries I equals 5.0 amps. Okay. What we want to find is A, the current density, assumed uniform. Assumed uniform means basically we can jump from that I delta Q equals delta Q over delta T equals negative NEAV to just straight the J formula. So that's really what they're talking about there. With part B, it says they would like to know the drift speed of the free electrons. And then part C, it would like us to find estimate the root mean square speed of electrons at 20 degrees Celsius. So we can get an idea of whether that velocity is very impressive. So I'm going to do V root mean square of E minuses at 20.0 degrees Celsius. So that's what we're trying to actually solve. I'm going to start off with solution. Now, what we need here is we need the J formula, which is equal to I over A. That can help us for starters. We also need the J equals negative N E V drift as a velocity, and we need to figure out what N is. N equals the number of free charges per unit volume. And that's a property of the material. Okay. So we need that so that we can figure out N. We do know, of course, what E is. E is equal to 1.602 times 10 to the negative 19th coulomb. So we know that. And what we're trying to get, of course, are these things that I listed before. So for part A, I'm going to say J is equal to I over A, which equals 5.0 amps divided by pi d squared, which is 3.2 times 10 to the negative 2, oh, negative 3 meters. Let me fix that a little better. So I'm using the formula in terms of the diameter, and I happen to know what that is, but this is 3.2 times 10 to the negative third meters. That's going to be squared. And then what happens is it's pi d squared over 6. So the 6 is going to come up here. So I'll write right here A equals pi d squared over 6 because that's another formula we just used. So now what I'm going to do is I'm going to take 5 times 6, and I'm going to say divided by parenthesis 3.14159 times 3.2 times 10 to the negative 3, and I'm going to square that number, and now I'm closing off my parentheses, and this gives me a really huge number. It's 9.325 times 10 to the 1, 2, 3, 4, 5 times 10 to the 5th amps per square meter. Obviously, we only had 2 sig figs, so the 2 and the 5 are extra. That is what J is. And of course, in part A, we were supposed to find J. So there's J. We're also using the fact that we're assuming it's uniform. So by setting it equal to a constant, that's another way of saying it's uniform. So there's one of our answers. Now, what they also want to do is find out, oh, we did that one. That's part A. So now we're wanting to find the drift velocity, but to do that, we've got to figure out what N is. And that's the part that I said was kind of tricky. But once you do it once, you just sort of either memorize the formula, or I think I might even put it on your equation sheet. But basically, N, we should be able to get that because if we realize that copper, oops, copper allows about, whoa, about one free electron per atom. So that's something we know. And in fact, it gave it to us in the actual instructions for solving this problem. It says, assume that one electron per copper atom is free to move, the others remain bound to the atom. And that's generally what we do with a lot of different metals, but some metals we have more evidence to suggest that maybe they release only make a half or a quarter of an electron, and some might produce 2 or 3 electrons, that sort of thing. So you basically would try to look that up if possible, but otherwise we have to give it to you. So now that we have that, we can say, well, if I think about the density of copper, that could come in handy. That relates the mass to the volume, and we do need a volume. So N is supposed to be a number over a volume like this. So that means we might need the density of copper, which I thought I knew off the top of my head. Oh, yeah, 8.9. No, I didn't know off the top of my head. I just looked it up real quick. 8.9, that's times 10 to the third kilograms per cubic meter. That's what the density of copper is. So that could relate to actual mass, but mass doesn't help us figure out the number of electrons or the number of atoms, which is what we need first. But what we do know is 1 mole of copper weighs, and I'm using that in the sense of grams, not kilograms and not newtons, but 1 mole of copper weighs 63 point, I think it's 63.5, ain't it? Yeah, 63.5 grams per mole. So if we just imagine a whole mole of copper, then it has Avogadro's number of atoms and therefore Avogadro's number of free electrons. So if we took 63.5 grams and converted that to a certain amount of volume, and then we could take Avogadro's number and just divide it by the volume, and we would have the number of free electrons per unit volume. So I'm going to say N is going to be Avogadro's number, and Avogadro's number should be divided by uh, the actual volume. And since density is equal to mass over volume, we can say that volume is equal to mass over density. So I can take and basically divide by mass over, or divide by volume, and that becomes Avogadro's number. And then that's going to be times rho, and then divided by the molecular weight, which I'll use a capital M for. So I'm going to say this is 8.9 times 10 to the third kilograms per cubic meter. That's the density. Avogadro's number is 6.022 times 10 to the 23rd. Now, that would normally be just reciprocal moles, but when we're talking about moles of copper, we would say atoms per mole. That's how we could sort of customize the units, if you will. But in this case, since we're using the fact that each copper atom corresponds to 1 electron, we can say E minuses per mole, like that. So that's the top two numbers. And then I'm going to divide all that by 63.5 times, now that's grams, remember, and it turns out to be grams per mole, but I got to convert that to kilograms. So I'm going to say 1,000 grams is equal to 1 kilogram. And now that, of course, already had units of grams per mole, like that. So now what you can see is the gram cancels out with this mole cancels out with this mole, and this kilogram cancels out with this kilograms. So I'm left with electrons per cubic meter. So I'm going to take 8.9 times 10 to the third times 6.022 times 10 to the 23rd divided by parenthesis 63.5 divided by 1,000. That's going to give me n, and that turns out to be, oops, supposed to be in purple here. That turns out to be 8.44 times 10 to the 28th. E minuses per cubic meter. So that's a pretty big number, and of course that's indicative of a cubic meter being a big chunk of matter and atoms being very, very small. So yeah, that seems pretty reasonable. Now we're prepared to actually find out what the drift velocity is, because we know what J is, we know what N is, we know what E is, so we can set them all together. We're going to say J in magnitude is equal to NEVD, and that's going to give us 9.325 times 10, and we're sort of estimating. So me carrying sig figs and stuff, that's really goofy, but that's just a habit I have of trying to keep it straight for you guys. So ignore it. So that's amps per square meter for J. The other side is going to be 8.44 times 10 to the 28th, and that's E minuses per cubic meter times 1.602 times 10 to the negative 19th coulombs. Again, estimating I shouldn't have used more than 2 sig figs. That's plenty enough here. Now all I have left is the drift velocity, which that just erased because the stupid good notes are not that good. So that's the VD. And from this, we can say VD is going to be a very, very small quantity. You're going to be surprised at how small it is, probably. Sorry, I'm going to explode that a little bit so I can erase it. Now I'm going to do the calculation. I'm going to take the 9.325 times 10 to the 5th, and I'm going to divide that by the 8.44 times 10 to the 28th. And then I'm going to divide that answer by 1.602 times 10 to the negative 19th. And that gives me 6.9 times 10 to the negative 1, 2, 3, 4, 5. So 6.9 times 10 to the negative 5th meters per second. So that's like on the order of microns per second. Way, 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 way slower than you might have expected. The last part we're supposed to do for part C is figure out what the root mean square velocity on average for the electrons is. I'm going to do that. Basically, what we know is 1/2 mv root mean square squared, this is velocity now, is equal to 3/2 kt. So we can immediately get rid of the 1/2 and the other 1/2 as as a denominator. And what we find out is that the VRMS turns out to be equal to the square root of 3 kt over the mass of the electron. So the V root mean square for the electron is the square root of 3 times 1.3807 times 10 to the negative 23rd joules per Kelvin. That's the stuff, or that's the Boltzmann constant. And then the T has to be in units of Kelvin. It was supposed to be 23 or 20 degrees, so it's going to be 293 Kelvin. And then we got to divide it by the mass of the electron, which is 9.109 times 10 to the negative 31st kilograms. We would give that to you. I just happen to know it. So now I'm going to take the square root of this mess, and it's going to be, I'm going to use parentheses. I'm going to say 3 times 1.3807 times 10 to the negative 23 times 293. And then I'm going to divide all this by parenthesis. Oh, I don't need a parenthesis. I'm going to divide it all by 9.109 times 10 to the negative 31 and close off the parenthesis, which also closes off the square root. And that gives me 1.15 times 10 to the fifth meters per second. So 10 to the 10 times faster is the velocity of a thermal electron at 20 degrees Celsius compared to the drift velocity. The drift velocity, like I said, VD equals 5 times 10 to the negative fifth meters per second, can be written as, for instance, if I wanted to make it microns, I would divide by 10 and then I'd multiply this by 10. And what we'd get is 50 micrometers per second. That's how fast it goes compared to basically 100,000 meters per second. And that's a pretty big difference. So, anybody have any questions? Of course, you're free to go. Make sure you can put your first and last name in the chat box if you haven't already. We're done. We finished chapter 25. There is actually one example on there. It's the very last one, and we just use a microscopic version of Ohm's law, and that is J is equal to, excuse me, that's J is equal to sigma E. And that comes in handy as well because once you have J is equal to sigma E, you can actually use that to calculate uh, what the electric field is inside of a conductor when a current's running through it. You can look at that example. It's straightforward. There's probably one that I've already done on my YouTube channel, but thanks for coming, everybody. I will wait for the last person to leave in case anybody has any questions. Have a good weekend and stay safe. All right. Well, that looks like it then. I'll just remind everybody to say, let's say C example 25, read and know example 2515. Okay. And that's it. I'm going to stop sharing and then I'm going to say bye bye. Bye bye.